sound. Is everything okay for you guys? You can hear me?
Yep.
Think they can hear me. Yes, everything's good. So for those of you who are here for the first time, we're doing a logic and automatic reasoning reading group. And basically what we're talking about is this textbook that I've published. Actually, so what I'll do is I'll share my screen as usual. Okay. So mute this one as well. So what basically we're reading is this textbook here. It's called Fundamentals of Logic and Computation with Practical Automatic Reasoning and Verification. I do hear some echoing from my laptop, from my iPad. Okay, let me go back to.
Oh, you write down that one, it should work, fine.
Let me see again. Okay. So that video is off. That audio is off. So they should still be able to hear me. Okay, so this is a book we're reading. And I'll post that link to the chat again. And if you're connecting through a Griffith network, then I think you can download the PDF for free, so you know what we're talking about. But before we actually go back to the topic of the book, so last time we talked a little bit about ChatGPT's automatic reasoning capabilities. So we actually looked at so this question that we asked that says if A implies B, not C implies not B, and we know that A is true, then must C necessarily be true as well? So that was a question we asked to ChatGPT, which was using GPT 3.5, right? And then GPT 3.5 didn't give a good answer, right? So first of all, it gave the wrong answer, and its explanation is flawed. And then we tried to ask Bing, which allegedly used GPT-4, and it gave the wrong answer as well. But then I heard that, although Bing's chat was using GPT-4, it actually wasn't giving the same answer as the GPT-4 version of ChatGPT. So some of the students at NUS got the license of ChatGPT, so they can use the so-called ChatGPT Plus, which can choose the version of the model. So we went to GPT 4.0, we asked the same question, and you can actually see it gives a pretty good answer, right? So first of all, it gives the right answer, and then it gives an explanation, and in the explanation, it gives the steps of its reasoning, right? So if you are having difficulties understanding those steps of reasoning, that's okay, because we will be giving we'll be talking about a reasoning technique that will basically show you roughly the same way of reasoning that is shown here. But the essence is it's actually giving the correct answer, and it's giving the correct reasoning behind it. The explanation is also very good, makes a lot of sense. So it does have much improved reasoning capability compared to 3.5. So at that point, I was a bit scared, because we all know programmers will be out of their jobs in a couple of years. But the question is, will computer scientists lose their jobs as well? So, so I went to the book. I picked some more formulae for GPT-4 to reason about. And here's another example. I say A implies that B implies C, and A also implies B. And the question is, does A imply C? Okay, and in my book, this is one of the formulae that we've got here. So it goes A implies bracket, B implies C. Actually, was right here. And then A implies B. Then you should be able to answer that A also implies C. Right, so this is a valid formula. That's the second one in definition 1.13. And hello, how you doing? That's okay. So GPT 4.0 again give the right answer, and they actually give the correct reasoning of how to get that answer. I was very impressed. So I was a little bit, panicked. And then I went to, and I said, okay, so we probably need a longer formula. We need a more complicated formula to give it some difficulties. So I went to one of the earlier sections, right? And I found this formula in Lemma 1.1. It looks quite complex to me. So I said, okay, can ChatGPT solve this? Now the problem is, with a formula that complex, it's pretty hard for me to translate this to English. So I had an attempt to translate that into English, and then ChatGPT understood my translation sort of incorrectly. But then it gave the correct answer. So apparently something's off there, right? It didn't understand my question correctly, but it gave the correct answer. And its explanation is again flawed. So I asked it again with a different way to frame the question, and now it gets a question right, but it gives a wrong answer. I see it says I mean, you don't have to read all those paragraphs. It says, in the end, it says, we cannot determine the certainty whether Z is true or not. It cannot determine. So apparently, if we make the formula complex enough, it still poses some challenge for GPT, even with, the latest 4.0. That was happy. So I know I wouldn't be, out of my job in a couple of years. Not yet, right? Not yet. And then I just went, okay, I won't ask the question in English. I'll just ask the question, does the left-hand side of that formula imply the right-hand side? And then GPT 4.0 started to apply some algebraic laws, De Morgan's law. And that was quite smart. See, those are exactly the same way that I did the steps here, basically the same as what I did there. I was like, okay, it is quite smart, and it's doing, it's applying the right things, right? And except, well, okay, maybe I should start writing something here. So what is De Morgan's law? De Morgan's law says if you've got not A and B, De Morgan's law says that is equivalent to not A or not B. Right, says you can put the negation together with A and with B, and then you have to flip the and to an or. And it is the same with not A or B. Right, if you have not A or B, then it's equivalent to not A and not B. Right, so you can push the negation into the bracket, into each component of the bracket, but then you have to flip the and to an or if it's an or, you flip it to an and. So that's the De Morgan's law. And if you look at how ChatGPT 4.0 did it, this says it's going to apply De Morgan's law to the last component. Let's see if I can draw something. Can I edit? I draw, I cannot draw. Okay, cannot draw. That's a pity. Okay, I think I can draw if I take a screenshot. Okay, so now I can draw. So it says it's applying De Morgan's law here. Okay, and how would we apply De Morgan's law there? We're gonna push the negation inside, but we're going to flip the or to an and. So we're going to get not z, not z, and not z or u. Okay, and those double negations eliminate, they cancel each other. So in the end, we get something like this, right? But then if you look at how ChatGPT 4.0 did it, it didn't get the same thing. It did flip the or to an and, so that's correct. But then it added some negation there. So it's trying to apply the algebraic law, but it didn't do it correctly, which is very interesting. And then since it didn't do the first step correctly, so the rest of it is not correct. And in the end, it still said it couldn't prove that, the left-hand side implies the right-hand side. So we almost lost all of our jobs, but currently we're safe, right? So at this moment, we're safe until they have, until 5.0. All right, so last time, I promised that this time we're going to learn about a new reasoning technique that is more systematic. So that would be basically, the same way of reasoning as what ChatGPT explained here. That would be roughly the same style of reasoning. Okay, so this technique is called, let me see where this free form thing. Okay, and to get more space. Okay, so I'm gonna put everything here. So this reasoning technique is called natural deduction. Okay, it's called natural deduction. And the reason why it's called natural deduction is because the guy who invented this this reasoning calculus was trying to emulate how human beings do reasoning with logic. So he thought, okay, this is a natural way of doing reasoning, and then he called it natural deduction. And in the literature, it's also called NK. It's not called ND, it's called NK. So apparently that guy's not English.
Like how I like FP and
Yeah.
literature makes no sense.
Right, and I'll show you who that guy is.
And gold is a
Guy's called Ginton. He was called, spelled his name wrong. So that was him. So he's German. That's why it's not called ND. Right? That's why it's called NK. But he was very, very smart. And so you can see actually in the first paragraph, introduction says he's the guy who invented natural deduction as well as sequent calculus. And I think in our reading group we'll talk about both of them.
he died young.
He died very young. I think he died when he was 35. Died of starvation. It's crazy. Yeah, I think if you read onwards, somewhere in his life, it's pretty sad. Starved to death. It's probably the worst way to die. But anyway, this guy's a good mathematician, regardless of everything else. So natural deduction. So that is our main topic today. So how do we do reasoning in the most natural way? In natural deduction, it's a proof calculus, or sometimes we say it's a proof system. So that proof calculus is made of a set of inference rules. Okay, it's a set of inference rules. So what is an inference rule? So we need to first set up what's the format of an inference rule. An inference rule usually is written in the way of premises. Premises 1. I'll just say premise 1. Premise 2. ... You can have more than 2, right? So, and then below the horizontal line, we have the conclusion. And that's usually the format that we write things. Above the line, we have the premises. Below the line, we have the conclusion, right? So what the rule represents, so somewhere we'll write the name of that rule. What the rule represents is above the line are the things that you assume is true, or they are the things that you have already derived in your previous derivations. Okay, so but in any case, above the line are the things that you know is true. And below the line is what you can derive from what you already know. That's the idea of an inference rule. Okay, this idea of an inference rule. And I think we can have an example from one of the very early sentences we've had. It's actually here. All men are mortal. Socrates is a man, therefore Socrates is mortal. Okay, if we write those in this format, it would be all men are mortal. Okay, so that's one of the things we know. And Socrates is a man. Okay, that's another thing we know. And then we get some conclusion. Right? The conclusion is Socrates is mortal. Okay, so above the lines are things we know is true. Below the line is what we can derive. All right, so that's the format of an inference rule. And with all those inference rules, in natural deduction, we actually divide them into 2 types of inference rules. One type is called the introduction rule. So an introduction rule introduces a new logical connective into the formula, okay? Introduces a logical connective. And then there's another type of rule called the elimination rule. The elimination rule eliminates a logical connective. Right? So one introduces a connective, one eliminates a connective. Right? So we're going to see those examples. All right, so they are the duals of each other. So we're going to see some examples. And we're going to go from the easiest one. We're going to go from the easiest one. Basically, it's almost a case that we'll have an introduction rule for a logical connective, and then we'll have an elimination rule for that logical connective. But for the case of, so we go from the simplest case, which are the logical constants, right? So truth. The introduction rule for truth, right? So it's called truth. With truth, I write a T for the top, means truth. And I means introduction for that concept. So what do we need to introduce truth? What do we need to know that truth is true? Well, this is obvious. We don't need anything. So this rule is extremely simple. And it just says from nothing on the top, we can derive truth. Okay, we don't need anything to derive truth. That's the idea. That's truth introduction. We can introduce truth from absolutely nothing because it is true. Okay. But
can I use any examples if I get questions wrong?
Hmm?
Can I say that my answers are correct?
Okay. Yeah. Well, do you have a Oh, so you mean in your exam? Well, this rule is trivial, right? It says from nothing you get truth, but
Yeah.
just because you get truth doesn't mean you get the right answer you need to answer the
But this
question,
is
right?
true.
Truth is always true, right? But it doesn't mean your answer is true. Those are two different concepts. So
I guess like my markers.
yeah, I don't think it will work. So we have an introduction rule for truth, but usually we would have an elimination rule for the same thing, except if you know that truth is true, how do you eliminate truth? Well, you cannot, because truth is true. So you cannot eliminate truth. All right, so there's nothing you can do to eliminate truth. That's why for truth, there's only an introduction rule. There's no elimination rule. You cannot eliminate truth. Okay. So that's everything we need to know about truth. All right. And the scenario for falsity is the exact opposite. Okay. It's exact opposite. So if we have falsity, I write, an upside down T for those who are here today for the first time. If we have falsity in our premise, what can we derive? So this is something that we talked about in the previous sessions. If you assume something that is false, you can derive anything. Right? You can derive anything. So if you have falsity as one of your premises, let's say you can derive a logical formula A, and you actually don't care what A is. A can be anything. If you assume falsity, if you assume a wrong assumption, you can derive anything you like. Okay, so that is falsity elimination. Falsity elimination. So we eliminate that falsity in our reasoning. Okay, but we cannot introduce falsity. We shouldn't be able to introduce falsity because falsity is false. It's never true. Right, so that's why falsity doesn't have an introduction rule, but it has an elimination rule. Right, so that's a dual of truth. You can see the symmetry here. You can see the duality here. Okay. So those are what we need to know about truth and falsity. Let's have a look at another easy example. So let's have a look at logical connective AND. Okay, let's have a look at AND. So again, we go with introduction. The introduction says there's some premises, but in the conclusion we want to conclude A and B, right? So we want to derive A and B. So the question is, what do we need to know to derive A and B? Well, we need to know that A is true, and we also need to know that B is true. Okay, so we need two premises. In this case, we need to have A, and we also need to have B. If we have both, then we can conclude that A and B is true. Okay, so this is the introduction of AND. Okay, introduction of AND. It should be very straightforward, right? So you know that A is true, and you know that B is true, then you can introduce A and B. Conversely, let's look at how we eliminate AND. So if you know that A and B is true, what can you derive? So what is true in the conclusion? All right, so, but okay, so in being elimination rule, we want to eliminate this AND. So from A and B, we can conclude that A is true, obviously. Okay, we can conclude that A is true. We can also conclude that B is true. There we go. So from A and B, you can also conclude that B is true, and that also eliminates the AND. But we want to distinguish them, so I'm going to add a subscript L to say we keep the left part, And here I'm going to add a subscript R to say we keep the right part. Okay, and that's how we eliminate an AND. Okay.
So there only ever be one. If it's true, can there only be one item underneath?
That is, yeah, well, that is what this rule is about. So if you want to derive that A is true and you want to derive that B is true, that you can do that, right? So in our reasoning, if you already know that A and B is true, you can, it's the same as knowing A and B is true as many times as you like, right? So we don't have the concept of something is true once or twice or something, right? So you can always use this rule, use this A and B is true, this statement as many times as you wish. Okay, so you can derive A, and separately you can derive B, and then you can do something about them. Okay, and there's something else that is not to do with any logical connective. It says from absolutely nothing, we can derive, or we can have an assumption, right? We don't need anything to assume that something is true. So from nothing, we can have an assumption. And in natural deduction, in the way we write it, whenever we have an assumption, we write it in square brackets. And then we also give it a name usually. So I'm going to call it A. So this lowercase a is a name of the assumption, and this capital A is a logical formula, right? So from nothing, we can assume that A is true, right? But obviously, when you finish your reasoning, you don't want your reasoning to have these kind of assumptions, right? So as part of your reasoning, you need to, there's a process called discharge your assumption. It says that the assumption can go, right? So when you finish your reasoning, you want to discharge all your assumptions, and that means you finished reasoning. Otherwise, if there are assumptions that are not discharged yet, that means your reasoning depends on that assumption, and that means it's not always true, right? That means the truth of what you want to derive depends on something else, right? We want, so what we're doing here is we're doing theorem proving. So if you think about theorem proving, it's about proving a formula is valid. Formula is valid means it's true in all the cases. So we don't want the truth to be depending on something else. So we want to discharge all the assumptions. Okay. Now there are a few other rules. So I'm going to go with the negation first. Negation is quite common. So the rule of negation, we have first we have let's say negation introduction, right? Negation introduction. How do we introduce that not A is true? How do we conclude that not A is true? Well, the way we do it is we're going to assume that A is true, and we're going to do some reasoning. So I'm going to write dot, 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 dot. So those are some reasoning. And through the reasoning, if we can deduce falsity, then we conclude that not A is true. So we assume that A is true, we deduce a contradiction, then A is not true. This is the idea. Okay, so this is negation introduction. Assume that A is true, deduce a contradiction, then we conclude A is not true. Okay, it is actually the same technique as so-called proof by contradiction. Right, proof by contradiction. And proof by contradiction also goes the other way. So dually we would have negation elimination. Okay, and the way we do negation elimination is quite similar. So let's say we have a not A. Assume that not A is true. And through some reasoning, we deduce falsity. So falsity is a contradiction. Right, we deduce a contradiction, and then we can conclude that A is indeed true. Okay, you get the opposite of what you assumed. whenever you derive contradiction, you can get the opposite of what you assume. Okay, so that's another form of proof by contradiction, right? So those are called proof by contradiction, which is a very widely used proof technique. Okay, it's called proof by contradiction. And there's actually a name for another name for this inference rule, negation elimination. It's called I need to spell that right. I need to spell that right. Don't spell everything right, but I need to spell something. Some of those guys right. It's called reductio ad absurdum. It sounds like a spell in Harry Potter. Like you've got a wand. Reductio ad absurdum. Okay, aka RAA, all right, RAs. So what that means is reduction of absurdity, right, essentially. And that's also, proof by contradiction. So that's how we deal with negations. That's how we deal with negations. All right, and then what else do we have? We also have implication. So we want to have an introduction rule for implication. We want to have an elimination rule for implication. Okay, so how do we introduce implication? So we want to derive A implies B. Want to derive A implies B. How can we derive A implies B? It's actually quite straightforward. It's very natural. The way we derive A implies B is we assume that A is true, and then we do some reasoning, we derive B. And then A implies B, right? That's straightforward. Assume that A is true, derive B, then A implies B. Okay. Oh, by the way, so every time, in all of those rules, after you get the conclusion, what you do is you discharge the assumption there, right? So I just say discharge this A, right? This A, so A, we always call it A in those things, but in reality, they can be A1, A2, A4, B1, B2, B4, whatever you call them. So yeah, so that lowercase a is just a name for that assumption. Yeah. It's just a name. All right, so that's how you introduce implication. But what do you do if you want to eliminate implication? So if you have an implication as a premise, the way you can eliminate it is actually when you also have that the left-hand side is true. Okay, so you know that A implies B. If A is true, then B is true. And you also know that A is true. Then what can you derive? Can derive that B is true. Okay, so you need two premises. You need to know that A is true. You need to know that if A is true, then B is true. Then you conclude that B is true. So in that way, you eliminate the implication. And this one also has a Latin name. It's called modus ponens. Modus ponens. Sometimes it's called MP. Very important. Okay, so that's how you do introduction and elimination for implication. Now, I think the last logical connective we have is or. Right, so we've talked about and implies negation, truth and false. Or is the last one. And I'm going to go with or introduction first. Because if you think about and or, they are sort of dual to each other, right? So their duality is everywhere in logic. It's designed to be symmetric. It's designed with duality. So the introduction rule for OR is actually symmetric to the elimination rules for AND. Okay, it goes, how do I introduce an OR? So we want to know that A or B is true. What do we need to know to derive A or B? Either one of them is true, all right? So if you know that A is true, then you can derive that A or B is true. If you know that B is true, you can also derive that A or B is true. All right. And again, we're going to distinguish them by saying this one is deriving A or B from the left-hand side, and this one is deriving A or B from the right-hand side. That's the introduction for OR. Okay. Right, so last inference rule in this whole calculus is the elimination rule for OR. And this one is a little bit tricky. This one's a bit tricky. So we want to eliminate OR. Right, let's say we have A or B. We have A or B. What can we get from A or B? It's actually quite tricky to think about what you can derive from A or B. But the idea is, let's say if you assume that A is true, let's have a A1. If you assume that A is true, you can derive something, let's call it C, another formula. Assuming that A is true, you can derive C. Okay. And let's have another one. Let's say there's another thread of reasoning. You assume that B is true. You derive the same thing. Okay. And you also know that A or B is true. So at least one of them is true. Then what can you derive as a conclusion? So C must be true. All right. So you know that if A is true, then C is true. If B is true, then C is true. At least one of A or B is true. Then C must be true regardless. Okay, so this is how we eliminate an OR. So, and then once you derive C in the conclusion, you can dismiss there's two assumptions, A1 and A2. Okay, what was your question? If they're both not true, if A is not true and B is not true, then A or B would be false.
Yes, okay.
So we don't talk about that because we assume that A or B is true, right? So
Yeah.
everything you put above the line is what you know is true.
Yeah.
Right? So we don't have that case here, right? But what is this proof technique though? So I'm sure you all do this all the time, you know, from primary school to up until now. This is actually just called proof by cases. It's called proof by cases. Right? Says you have many cases. It could be A, or it could be B, and then for each case you derive what you want, and then what you want is true. Right? It's called proof by cases. So you can also generalize this to, you know, or D or something else. You just need to have all of them here. They all derive that C is true. Right? It's proof by cases. Except right now, we can simplify it to just two cases. Just two cases. It's called proof by cases. Okay, so these are everything in the natural deduction calculus. Right. So that calculus is different than the calculus that Newton's invented. That calculus is used for, you know, integration and differentiation. This calculus is used for reasoning, right? But they are called calculus. There are actually a lot of different calculi. I think that's
So many.
Are they at odds with each other with any of the theories, or do they all just like have a different part of the same picture?
They're I think most of them are for different theories.
Yeah.
So they don't really play with each other.
Yeah, okay,
Alright.
yeah.
They don't really play with each other. So they're for completely different things. And then Gentzen, this guy who invented natural deduction, proved some very nice properties about this calculus. So the two important properties. One is called soundness. The soundness, being soundness, it means the calculus is correct. Right? It is correct. So the formal definition is if a formula, call it F, can be proved using NK, so NK stands for natural deduction, then F is valid. Right? It says if I can prove this formula using my system, then it is indeed valid. So it means my system is correct. So the other one, the other nice property is called completeness. Completeness goes the other way around. It goes if a formula F is valid, then it can be proved using NK. So it says I can prove everything that is valid. That means that's why it's complete, sound and complete. All right, those are the two very fundamental properties for a proof calculus. So if you want to have a new proof calculus, it better be sound and complete.
So I try and make one of them.
So, people are making new ones every day, unfortunately, but you don't have to learn all of them, right? But this one is one of the very early ones. I think it's funny because, people have been using this kind of classical logic for thousands of years, but then was not until 1930s when this guy invented the two calculus that are sound and complete. Right? So it's arguably one of the very earliest, we call it systematic proof calculus for classical logic. And now we can use it to prove some examples, right? So we have 10 minutes left. Let's do one example. So let's do that example with ChatGPT. There was this one. That's this one. It says A implies B, and this one's actually quite complex. But we can break it down a little bit. Not C implies not B, and A is true. And what about C? Okay. So example says A implies B. Okay. It's only about truth. And not C implies not B. Okay. Not C implies not B. And we also know that A is true. The question is C true? Okay. That's the question. So we can use some of the inference rules we had just now. All right. So remember, how do we eliminate implication? We have A is true. We have A is true implies B is true. We can eliminate the implication by concluding that B is true. Okay. Yeah, it takes A, and it also takes the implication out of the question. So now we know that B is true. Okay. Now we know that B is true. Okay. So now what do we do? So we know that B is true. Now the question is C true? So how about let's assume that C is not true? Okay. Let's have an assumption. Assume that C is not true. What can we derive from here? Well, we have not C implies not B. Yeah. So not C implies not B. And again, if you apply the implication elimination, what do you get? You get that not B is true. Okay. Right. So, right, that's the same format as what you get on the left. Okay. And now what do you know? You know that B is true. You also know that not B is true. That's impossible, right? That is impossible. So what do we call this? We call this a contradiction, right? Contradiction is falsity. So we derive false. Okay. And now let's have a look at the negation rule. So we've got the negation rule somewhere here. It says you assume that not A is true, and through some reasoning you derive negation. Then what do we get? We can conclude that the opposite of the assumption is true, right? So A is true. And that's negation elimination, or REA. Okay, let's look at what we've got here. We assume that not C is true. And so this is the whole thread of reasoning. We derive, contradiction. So what can we do? We can do negation, elimination, and conclude that C is indeed true, right? And by doing that, we also discharge the assumption A. Okay, that's part of what's happening here. So you derive falsity, and then you discharge the assumption. You get the opposite of your assumption. Okay, and so now that assumption's discharged, every time before we finish a proof, a thread of reasoning, we always have to check if do we have undischarged assumptions. Okay, so now we don't have any undischarged assumptions, and so our job is complete. Because if you have undischarged assumptions, then the truth of whatever you derive depends on that assumption, right? So we don't want the truth of what we want to prove depends on anything. So now the job is done, right? So C is indeed true. Okay, so that's the reasoning. And once you understand that, you can actually read whatever that is given here as ChatGPT. It actually makes a lot of sense with GPT 4.0. Actually, it goes roughly the same way as how we did the reasoning there, except it gives you the reasoning in English.
Oh, and it's good at doing practice stuff. No, let's try drinking here.
Okay, so it's doing the same reasoning in English. So that's the example. Do we want to do another one? We have 7 minutes. So this one says A implies that B implies C, and A implies B. The question is, does A also imply C? So this is a bit hard to understand here, right? So A implies that B implies C. Okay. So what we should be writing there is A implies that B implies C. That's what the first part is about. Second part says A implies B. Okay, A implies B. And the question is, does A imply C? Okay, so we also know that A implies B. And the question is this. That's what we want to know. Okay. So you see, now what we want to know is A implies C. So what do? We want to introduce that implication. We want to introduce that implication, all right? So how do we prove that A implies C? We assume that A is true. And through some reasoning, if we can derive C, that's okay. Yeah. if we can derive C, then we can conclude that A implies C. So that's exactly implication introduction, and discharge the assumption A. Right? We call it A1 just in case we will have some other assumptions along the way, but that's how we do implication introduction, right? So now we just need to fill in the blank. We just need to fill in the blank. Okay, let's fill in the blank. So we know that A is true. It's assumed true, right? And what can we do? Well, there are a bunch of things we can do. So we've got two implications there, and the left-hand side are both A. All right, so we have A implies B implies C. And from these two, we can derive something. So that is implication elimination.
But won't the top get damaged and then
Okay. That's implication elimination. But we have two implications there. We have two implications there. The one we eliminate is this guy here. Yes, so after we eliminate it, what can we conclude? We conclude the right-hand side. Right, that's always what we do. Right, so if you look at this, we know that the left-hand side is true, we conclude the right-hand side. Right, so we conclude the right-hand side, which is B implies C. Okay, so that's the first thing we can do. And now we can do something more. So, okay, we've got this assumption. This comes back to your question, what if I want to use it twice? You can use it as many times as you like. So you can actually copy that here. And that's the same assumption as that one. So I give it the same name, A1. Okay. You discharge both. Right?
Oh, okay.
So we know that this is assumed true. We also have A implies B. Okay, we also have A implies B. So what can we conclude? We can conclude that the right-hand side of the implication is true. So B is true. And that is, again, implication elimination. And now we can apply the same rule on these two. So you know that B is true. You know that B is true implies C is true. So again, that's implication elimination. You can conclude that C is true. Actually, that's exactly what you need down there. All right, that's exactly what you need down here. So actually what I can do is I will move those guys a bit downwards so they align well. Okay, now they align well. Okay. And remember here we discharge A1. So those two assumptions again. And think our job is finished. Okay. So that means this guy is true. This guy is true. Can you derive that A implies C? You absolutely can. Okay, you absolutely can derive that A implies C. And if you read the reasoning here, it's basically doing the same thing. But it's doing the same thing, not with symbols, but in English. So, GPT 4.0 is quite smart. It is quite smart. It's getting there. It's getting there. It's going to eliminate human beings one day. Well, up until it gets this very complex formula, then it doesn't get it right. So,
Yeah.
so that's our last hope. That is our last hope. But actually, the way I analyzed this case where GPT 4.0 get it wrong, it's trying to apply some rules. It's not doing natural deduction, but it's trying to apply some algebraic rules. And it almost got it right, but it put the symbol in the wrong place. So it seems as if it's not really doing the formal reasoning that we're doing, but it's trying to put the symbols in the most plausible places in the sentence. That's what it's doing. And sometimes it doesn't get it accurately, so it puts a symbol in the wrong place, so it gets something wrong. All right, so it gets something wrong. All right, so remember when we talked about the proof calculus, it usually has two important properties. Soundness says it has to be correct. It must be correct. Completeness, it must be able to prove everything you need to prove. So I think soundness is usually what AI, this kind of machine learning based AI is not good at. Because those AI models always have the problem of accuracy. Soundness requires accuracy is 100%, which is not possible for most of the AI models. But that's what's required for automated reasoning. So you can see those are actually two different ways of doing things. Two different ways of doing things. And my recent idea is actually to sort of combine them. So I think I'm going to have a new research project. If you think about what ChatGPT is really good at, it's really good at processing natural language. That's what the model is for.
Yeah.
Right? And automated reasoning is really good at processing symbols and doing reasoning that is guaranteed correct. So what if we can ask ChatGPT, whatever GPT 4.0, to process, a paragraph of text into symbols, and then from there, automated reasoning takes over and does the reasoning and guarantee correctness. Okay, so that was the idea. So what I actually did was I think I sent sort of. Do I have that email somewhere? Okay. So the other day I sent an email to actually my PhD supervisor when I was doing my PhD. So I said, yes. So I said, okay, what we asked GPT to do is to process language, English language into symbols. So one of the application is, we look at those movies, TV series, we look at their scripts. A lot of scripts would have plot holes, would have loopholes, right? And I went to one of those movies called Glass Onion. It's actually a pretty good movie. It's a good one, yeah, a very good one. So I went to the, summary of the plot, synopsis. So I copied this whole thing, this whole, paragraph, many paragraphs of text into ChatGPT. I said, can you summarize this into a logical formula? And it actually does it. It does a job. It doesn't do a correct job, but it does a good enough job. It does a job. So you see all those highlighted parts. So those are all generated by ChatGPT. So in the end, it actually gives you a formula that summarizes the plot. Okay. So I put that formula into Isabelle Hall, and it's got some syntax errors, but easy to fix. Right. So I fix it, and then I can ask Isabelle, check if there's a loophole. All right. So that's some application. And you can apply the same to, let's say, laws. You got laws and you want to see if there are loopholes in our, laws and regulations. You can actually do the same with, I'm thinking, if you have a criminal suspect records and whatever they say, and check if what they say have, logical contradictions. So I think that would be an interesting direction to go in the future for now. Yeah. Combine that with automatic reasoning. So okay, yeah, we're actually gonna be over time. I think yeah, that's everything we need to talk about today. So thank you very much.
Thank you.
Nice.